All right, so we have a very important topic today, differential cryptanalysis. So my aim is to give the idea behind differential cryptanalysis, then explain how these differences affect each layer of a block cipher by focusing on present. Then I will show you how you can find these differential distinguishers for present and then try to recover round keys by using those distinguishers. So let's start. So before start, of course, let's recall what present looked like. Recall that we had 64-bit input. Each line represents 1 bit. At the key addition layer, we simply XORed round key of 64 bits. Then we had a single S-box, right? And this S-box is fixed and it is, done in parallel 16 times. Then we switch the places of the bits, which is simply a permutation, okay? So with the differential cryptanalysis, we will focusing on just flipping one bit in the input and then try to observe how this change affects each layer. Okay, so that is the idea behind it. So don't forget that in differential cryptanalysis, we work with pairs. So we have two inputs and we know the difference. So assume that we are encrypting two inputs, I and I prime. With difference, I XOR I prime equals to some value alpha that you know. Okay. So this is why we're actually going to tell this is a chosen plaintext attack, because we are choosing it, saying that their XOR should be alpha. I mean, I'm not imposing any condition on I. It can be anything random, but I prime should be I XOR alpha. We call that XOR operation. It's just modulo 2 addition, so you can take this I prime to here and put XOR here and so on. So now let's consider the effects of the key addition, substitution, and permutation layers. Key addition layer is simply you are XORing the round key K, right? So we are encrypting two different pairs. So after this key addition layer, the output will be I XOR K for one input and I prime XOR K for the other input. Since we don't know K, we don't know the results, right? But since both inputs are encrypted with the same key, in other words, K here, their difference is still the same. So I don't know these two values, the outputs, but if I XOR them, I know that their difference will be K will cancel each other. We will end up with I and XOR I prime, but we initially fix their difference to alpha. So we know that this key addition layer does not change this alpha difference. So this is actually why we are giving the difference in terms of XOR operation. So of course, this applies only when the key addition is simply an XOR operation, right? Let's move on to substitution layer. Now let's assume that I is just 4-bit S-box input, right? Or you can generalize it to the all of these S-boxes, but let's focus on a single S-box. So one of the input for an S-box will be I XOR K, and in the parallel, we are encrypting something else, and that's the input is I prime XOR K. Since we don't know these inputs exactly, we don't know what will be output when we perform the S-box operation, right? So this is a huge problem. So we cannot exactly know the differences of S with the input I XOR K, XORed with S with the input I prime XOR K. But we can analyze the S-box to see which input differences provide which output differences. So this is the huge trick. This is where we introduce difference distribution tables and see how an S-box manages with differential cryptanalysis. The whole idea of difference distribution tables come from this observation. So as you can see, substitution layer causes a problem to us, and we will approach it probabilistically. So this is where statistics will come into play. But we had a final layer called permutation layer. Let's look at presence permutation layer. It only changes the places of bits, right? So there's a permutation called P. So if the input is ith bit, the output may be jth bit something. We don't know. But I bit goes to the place of the jth bits. That is it. So if the input has a non-zero difference at the ith bit, then the output has a non-zero difference at the pith bits. So the bit flip you observe in the input, you observe it after the permutation. So as you can see, this is a linear operation for us. So this doesn't cause us any problem. This doesn't also cause us any problem, but only problem here is coming from the substitution layer. So this also means that if you remove all of these S boxes, for an input, assume that I have the plain text and the ciphertext. If I flip one bit, I will know exactly what will happen afterwards. The differences in what I mean. So actually the cryptographic security comes from the substitution layer here. So we have to deal with it. This is why we are going to focus on the S box and see what we can do about it. So we know the input for the S box, right? Whenever we have these inputs, the outputs will be this. So we know this. But the problem is that we don't know the key, round key. So we don't know, for instance, let's go back to the beginning. If I know these 4 bits, I don't know the round key of these 4 bits. So I don't know what will happen after the XOR. Since I cannot know these 4 bits exactly, I cannot know what the output will be. This is one of the problems. So for this reason, we will approach it in a statistical way. So consider every possible X and Y input pairs with X XOR Y equals to I. As you can see, I'm fixing the difference of 2 inputs. Now, count the output differences where SX XOR SY equals to J. So for each pair, repeat this process and increase the counter where you observe the value J. Construct the table with this count as the ijth entry. Okay, this is how we define a difference distribution table. So let me show you what presence difference distribution table looks like. So after you perform these operations, so if you choose X equals to Y, then SX XOR SX will be 0, right? So you can take X with 16 different values. So this will mean that you will, when you provide the, if you choose the input difference I equals to 0, you will always observe 0. So for this reason, 0th entry in the table is always 2 to the n, where n is the size of the S box. So if you create the difference distribution table for AES S box, since it is 8 by 8, you will observe 256 here. And the rest will be zeros. So we are not actually interested in the 0th column or the 0th row, okay? We are interested in the rest. So let's see what the rest means. So here's an example. If you have the input difference 4x, this means the 4th row, okay? This means that the output difference 5, let's go and find the 5th column. You observe the value 4. So out of 16 possible input pairs which have the input difference 4, you will observe in 4 of those cases the output difference 5. Okay, so this means that out of 16 possibilities, in 4 of them you will observe this difference. So this also means that if your S box input difference is 4, the output difference will be 5 with probability equal to 4 over 16, which is 1 over 2 to the 2, or in other words, 2 to the minus 2. Okay, so if these values are higher, the probabilities will be higher. If the probabilities are higher, I will more definitely know what is going on, right? So for the cryptanalyst, having higher values here is a good thing. For the designer, we want everything to be smaller. Okay, so there are 2 things that you can observe. Some things are impossible. For instance, if you give a single bit difference on the least significant bit, you will never observe a single bit difference here. So this also means like this. So what does the difference 1 mean? So if you choose an x equals to 0, then give the difference 1, you obtain 1. So your x, y pairs are these. So if you choose x equals to 2, if you XOR it with 1, you obtain 3. So this is another xy pair. This is another xy pair. So you pair them in 2s. This means that look at the output and XOR them. And this means that you will never see 1. So as you can see, C XOR 5 is not 1. 6 XOR B is not 1. 9 XOR 0 is 9, so it is not 1. A XOR D is not 1, and so on and so forth. So this is how you construct this table. So some things are impossible, so we observe zeros. But since we can choose x in 16 different ways, we will observe 16 output, right? So the sum of the values in a row have to give you the value 16. Also, sum of the values in a column has to give you 16. Okay? So, as I said, as a designer, I want to have very small values here. So what can we do? So best scenario would be having only zeros and ones, right? But you cannot have ones because look at the problem itself, okay? We are talking about XY pairs. So assume that I chose X and I equals to 1. So my XY pair will be 0, 1. But then if I choose X equals to 1, 1 XOR 1 is 0. Now Y equals to 0. So you just flip your X and Y values, but the output values will also be swapped, but their XOR will not change, right? So for this reason, these values has to be even all the time, okay? So again, for the designer then, what I can do is having only zeros and twos in this part. But as you can see, we have some values 4. Question is, could I find a better 4x4 S-box which only contains zeros and twos? Unfortunately, the answer is no, we cannot do that. Okay, so let me explain why this is the case. So the highest value in the DDT table, except the first entry, which I said it is always 2 to the n, is called differential uniformity. So if we go back, we observe 4s here. We don't see 6, 8, or anything larger. So we say that presence S-box is 4 differential uniform. Okay, its differential uniformity is 4. High differential uniformity provides characteristics with high probability. Hence, lower is better for the designer, of course. Higher is better for the attacker. Values in DDT is even because the pairs XY and YX provides the same difference. Thus, theoretically, the best achievable differential uniformity is 2. For odd n, we know ways to construct such n by n S boxes. So for a 5x5 S box, you can observe a DDT where you only see zeros and twos. But since we are working on bytes or nibbles, we generally prefer 4x4 S boxes or 8-byte S box. So question is, can I get a 4x4 S box which is 2 uniform? Unfortunately, there is no such S box because we traversed every possible S box. Of course, the number of possible S boxes are really huge, but we can, group them with equivalencies and then look at the equivalence classes and observe that there is no such an S box. So for a very long time, people thought that we cannot have 2 uniform even S boxes. So since we cannot find anything for 4x4, and AES has an S box 8x8, and it is also 4 uniform, it's a very nice S box. So people thought that maybe we don't have 2 uniform S boxes when n is even. But something strange happened. With a very special design, Dylan in 2010 found a 2 uniform S box, which is 6x6. So now the big open question is, can you find a 2 uniform 8x8 S box? So if you can do, it will be something better than AES S box in terms of differential cryptanalysis. So it is an open problem since 2010, and it is currently not being solved. And we cannot solve it by, brute force. We cannot try every possibility and see it because the space is really, really huge. So to explain why the space is huge, let's look at 4x4 S boxes. So 0 can go to 16 different values, right? Then this can go to 15 and so on. So you have 16 factorial different cases. But when the n increases, this number increases really faster and so on. All right, so let's look at design criteria for presence S box. So since the best we can get was 4 uniform, the present designers said that they wanted something 4 uniform. They also said that they don't want any fixed point. So for any x, you never see x equals to sx. So if you go back to the table. So 0 doesn't go to 0, 1 doesn't go to 1, 2 doesn't go to 2, etc. So you might think that this is obvious, but actually there are many lightweight designs where this thing happens. So in theory, this isn't directly a weakness, but in practice, actually, fixed points, especially in mathematics, causes most of the time a problem. For instance, in this case, this means that you are not actually changing the input, right? So this is like you are just bypassing this layer. This is why present designers avoided that. So they also chose a design criteria as follows. 1-bit input difference never provides a 1-bit output difference. So for XY, where the XOR is 1, 2, 4, or 8, you never observe an output difference that is 1, 2, 4, or 8. So this is important, and let me show you why this is and how you can see it from the DDT table. As you can see, if you look at the first row, 1 doesn't provide 1, 2, 4, or 8. So this is why you observe zeros here. Same thing applies for 2, 4, or 8. So this is important because as the attacker, my aim would be to, cause a small difference, like flipping 1 bit. So if there's an only 1-bit input difference, and if you observe 1-bit output difference with some probability, this would mean that this input difference will only affect after one round later only the same S-box, for instance, if the permutation is here, right? So assume that one input difference goes to one output difference with some probability. So in that case, only this bit will have the difference. So in every round, it will only affect itself with some probability. So for this reason, they try to have, if there's a 1-bit output difference, it should affect 2 bits. So these 2 bits after one round later will affect 2 S-boxes, and so on. So this would cause a better diffusion. Okay. So yes, this is one of the design criteria. So with this DDT table, now let's talk about how we can construct high probability differential characteristics. So we are focusing on the 4-round iterative characteristic of present one by one. So let's look how this works. So this table says that as the input, assume that you are only giving the input difference to 2 S-boxes where their positions are 0 and 3, with the input difference is 4. Okay. After the S-box operation, you observe the output difference as 5 for these 2 S-boxes with probability 2 to the minus 4. So let's see what this means. So let's go back to present picture. So for the 0th S-box and the 3rd S-box, you are giving the input difference 4. In hexadecimal, 4 means there is an input, so this bit is flipped, right? Also, this bit is flipped. So they say that the output difference, I'm not talking about the output, I'm always talking about differences, just focus on this. So it says that it will be 5 in hexadecimal, so it means that 0, 1, 0, 1. So it doesn't have to happen all the time, right? If we go to the DDT table, it says that when your input difference is 4, the output difference is 5 with 4 out of 16 cases, which has probability 2 to the minus 2. So for a single S-box, with this probability, I observe the output 5 difference. But since we have 2 S-boxes, we are assuming that these are 2 independent events. So observing 5 output difference in both of the S-boxes has probability 2 to the minus 2 multiplied with 2 to the minus 2, which is 2 to the minus 4. All right, so this is just for the S-box layer. For the permutation layer, these differences in these bits actually moved on to some other places, and it turns that they go to, again, to 0th S-box, but also the 8th S-box, but now we have 2 non-zero bits here and 2 non-zero bits here. They go to other places, and they turn into 9 if you follow the permutation. Okay, so now question is, if my S-box has input difference as 9, what can be the output with high probability? You again go back to DDT table and look at what happens when the input difference is 9. You observe that there are some 2s, but there's 4 here for the output bit 4. And the attacker just focuses on that scenario. Says that, okay, let's assume that the output is 4. And this again happens with probably 2 to the minus 4. Now you follow the permutation layer. Now we have single bit differences, as you can see. After the permutation, they go to these two S boxes at the bit positions here. Then you again look at the DDT and check what if the input difference is 1, what is the probability if the output difference is 9. Again, perform the permutation. Then again, it goes to two S boxes with input difference 1. So the only difference is, as you can see, until this part, we said that these events happen with probability 2 to the minus 4. But now I'm saying that this happens with 2 to the minus 6. So let's see. Input 5 difference provides output 1 difference. Go back to the DDT table. Input difference is 5, output difference is 1. This happens 2 out of 16 cases. So it is 1 over 8, which is 2 to the power minus 3. So since we are talking about two different S boxes, when you multiply 2 to the minus 3 with 2 to the minus 3, you end up with 2 to the minus 6. Then, after the permutation, these bit differences goes to these S boxes. So here we observe two things. Generally, this doesn't happen, but here we use the word iterative. This is because I started with the input difference at these two bit positions, and there were 0 differences on the remaining 62 bits. After 4 rounds later, I'm still at the same position. Okay, this is the same as this. This means that take this table, put it below it. Now you have an 8 round characteristic. So you can repeat it as many times as you want. So now the question is, what is the probability, or what does this table means actually? This table means that if you have a random input and flip only these 2 bits, 4 rounds later, you will see only differences at the same bit positions with probability, which is the multiplication of all of these probabilities. So in this case, it is 2 to the minus 18. So if you repeat this table twice, then you end up with 8 rounds characteristic, but this probability will be 2 to the minus 36. Right? So you can go this way. But of course, you cannot go forever, because at some point, the probability will be smaller than 2 to the minus 64, and 64 here is the block size, so it wouldn't make sense. Okay, so if we assume that these probabilities are independent, but actually they are not, by the way, because I mean, for independently for round probabilities, this is correct. But once we give the input, you know, some operations are applied to, so you can no longer say that at the second round the inputs are random. Actually, they are not random. They are, you know, affected by the previous operations. But we assume that they are independent. So if we assume that these probabilities are independent, then the 4-round characteristics hold with probability of the multiplication of all of the round probabilities, which is 2 to the minus 18. Important question, how can we obtain this probability in practice? So can I experimentally verify it? And the answer is yes. Just randomly choose many inputs, give them this input difference, randomly choose a key, encrypt all of them, then look at the differences at the ciphertext and repeat this process. As you can see, this is a binomial distribution in this scenario. See how many times you observe the expected output difference. So this question is important because in practice, it might be significantly smaller or larger than 2 to the minus 18. This is important. Most probably it will be higher because you observe that there is a path like this, okay? And assume that all of your assumptions are correct. So, you know, this path is followed with probability 2 to the minus 18. But here, I'm not interested in the intermediate values, right? I'm looking at the input difference and output difference. Maybe this input difference will give you something else in some scenarios. But after 4 rounds later, it will come back and provide you this output. This means that maybe there are multiple differentials that have the same input and same output, but with different probabilities. So if you sum all of those probabilities, that will be the correct probability. But since we don't have the computational power to traverse all by hand or by computer, what we can do is to perform an experiment and observe if it is higher or smaller than this. This is really important because in many cryptanalysis results, we obtain a lot of results theoretically, and most of the time people don't verify it in practice because it requires a lot of computational power, a lot of memory and data. But if you look at the shortened versions of it, those experiments might give you a better idea. And in the literature, actually, we corrected many wrong attacks when we tried to verify them experimentally. So experiments are really important for cryptanalysis. Okay, so input and output differences are the same for this example. So we can put the same characteristic below to obtain 8 rand characteristics with probability 2 to the minus 36. This is why we use the name iterative. So if you put again below this 8 rand, now you obtain 12 rand characteristic, but the probability will be now 36 plus 18. So it will be 2 to the minus 54, right? Okay. So distinguishing attack. This characteristic is actually a distinguisher for 4 rand present, right? So this is why we said that everything starts with a distinguisher. Okay, now I found the distinguisher. So how you can distinguish it? So for 4 rand present, this distinguisher holds with probability 2 to the minus 18, right? We calculated this in a theoretical way. But for a random permutation, it holds with probability 2 to the minus 64. You might ask why it is 64, because the block size is 64. So if you take a random permutation, okay, and give it 2 inputs like this, the output will have this output difference with probability 2 to the minus 64, because I'm explicitly saying which bits would have non-zero difference and which bits will have 0 differences. So for 64 bits, I'm forcing them to, I'm explicitly showing what will be the output difference. So this property holds with probability 2 to the minus 18 for rand present, but 2 to the minus 64 for a random permutation. Now you can see that we have 2 different binomial distributions with 2 different probabilities. Now we can distinguish it. So if we check this distinguisher, so I'm actually giving you a black box. I'm asking you if it is a 4 rand present or if it is a random permutation. All you can do is to give an input and look at the output. Recall our dice throwing experiment, okay? So if you check this distinguisher using n-plain text, so you are giving difference to these n-plain text, so you encrypt them with pairs. In other words, you give it to this black box and it look at the output. Then we will be trying to distinguish 2 random variables which are binomial distributions with parameters p0 and p. Recall that the expected values are n times p and n times p0 for these 2 different distributions. So if you perform this experiment with like n equals to 100, it wouldn't help you, because 100 times p is something really small, but 100 times p0 is also something very small, which is less than 1. So it wouldn't work. So you should at least choose n is larger than this. So c times 2 to the minus 18, let's say. So here I think n should be something like 2 to the 19 or 2 to the 20, so that this would be larger than 1, and so that you can try to distinguish these 2. Okay, so here is a very nice homework for you. So what you can do the following: experimentally verify the theoretically obtained probability. So I said that this holds with probability 2 to the minus 18, right? So the question is, what is actual probability if I really wanted to distinguish present? So let's denote alpha as the input difference to these 2 s-boxes, right? And beta will be the output difference. But for in this experiment, since it is iterative, alpha equals to beta. This wouldn't be the case most of the time, right? But for this example, this is the case. So you can do the following: randomly generate 100 keys. Then initialize 100 counters to these keys, okay? Randomly generate n-plain text pairs, n will be your choosing. Actually, it also depends your computational power. Perform 4 round encryptions on pi and pi XOR alpha, because these are the pairs, right? increase the counter of CI if encryption of PI XOR encryption of PI XOR alpha equals to beta, which is also alpha in our example. So here I'm doing it for 100 random keys because maybe this characteristic just by chance works better for a specific key, right? This is why you should randomly choose your keys and look at the average, right? So calculate the average of CIs and obtain the practical probability of the characteristic. So, of course, your implementation doesn't have to be like this. For instance, you can take this step above this and put this here, and it will be, probably would be easier to implement because you randomly generate the plain text encrypted with every 100 key you already pre-generated, and then, increase the counters. So at the end of this, when you look at the counters, so it will be the number of times you observe this output. So divide this average by n, it will give you the practical probability. So question is, will it be higher than 2 to the minus 18 or smaller than? Okay, so a very nice experiment to verify a theoretical probability in practice.